are in the last leg of chapter number 25. Okay, so today we should be finishing this particular chapter. So what we will see today is shell theorem. Okay, so let's see, there are two shell theorems. Let's see what they are. So the first shell theorem says that if you have a uniformly charged spherical shell, I hope you understand what that means. Okay, you have a uniformly charged, let's say it's positively charged. It's uniformly charged all over the surface. It has got a uniform charge, surface charge distribution. Okay. Then it says that shell means inside there is nothing. It's thin walled. Okay. So a uniformly charged spherical shell exerts no electrostatic force on a point charge located anywhere inside the shell. Let's say I have a point charge Q naught. Q naught may be positive, Q naught could be negative. Wherever you place it, anywhere inside this shell, Q naught will not be able to sense this charge on the shell. It will not be able to sense the charge on the shell. Therefore, the force experienced by Q naught will be equal to 0. So this is what shell theorem 1 says. So once again I repeat, if you have a spherical shell and the charge distribution is uniform all over the surface of the shell, if you place a point charge anywhere inside the shell, that charge will not experience a force. Okay, an analogy for this I will tell you from gravitation. In gravitation, I'm sure you must have seen some of these science fiction movies. So that would be based on the idea of the earth is there, the earth is a sphere. If you drill a hole through the air, the earth, and then reach the center of the earth, you will not feel any gravitational force. Same thing. Okay. So if you have a sphere of charge, a shell of charge, anywhere inside that shell, if you place a charge, that shell will not see this charge distribution. It will sense a zero force. Now let us go to shell theorem 2. Shell theorem 2 says that if you have a uniformly charged spherical shell exerts an electrostatic force on a point charge outside the shell. Let us say that the radius of the shell is r, then F is equal to 0 for all small r less than capital R. When I say small r, I am talking of the distance of Q naught from the center of the shell. So for all small r less than capital R, the force is 0. But the second theorem says that if your charge Q naught is outside, if your charge Q naught is outside and at a distance R greater than capital R, greater than or equal to capital R, then shell theorem says that your charge Q naught, the charge Q naught which is outside the shell, will now not be able to see this as a sphere. It will see this entire capital Q as a point charge. The shell will be seen as a point charge by Q naught. Q naught is outside that sphere. So Q naught will see the shell as a point charge. Point charge containing this charge Q. And where is this point charge? The point charge is located at the center of this shell. Or in other words, when small r is greater than capital R, the force will be simply equal to 1 by 4 pi epsilon naught Q naught Q divided by R square. That is this shell, the sphere will appear like a point charge Q. It will appear like a point charge Q separated from Q naught by a distance R. I hope this is clear to you. First shell theorem and second shell theorem. So simply if you have a uniformly charged spherical shell, any charge placed inside will not experience any force. But the minute you place that point charge outside, this outside charge will see the shell as a point charge. So that's what is shell theorem 2. Okay, or simply I can write it as a one single sentence. I can say the charge distribution with spherical symmetry can be treated as a point charge. Though it is a spherical charge distribution, the charge outside will see this spherical charge as a point charge. Okay, so let me see how many of you are in the class today. 22 only. Where are the others? I'm telling you, I am capturing the attendance. Those of you who don't have attendance will not write the examination because that is the communication given to us. So better attend the classes. Attendance is being taken. Acha, so all of you are putting your attendance there. Okay, put it, no problem. Even otherwise, I have ways of taking it. Put it. Okay, so now let's go to the next slide. Where is this shell theorem going to be useful? Let us see. That I will make you understand by working out the problem. Okay, so look at this. A spherical nucleus of, so though it is called a shell theorem, please remember a solid sphere is made up of many concentric shells. This is a very important point. A solid sphere is made up of many concentric shells. So keeping this idea in mind, let us work out a problem. A spherical nucleus of radius r contains Ze positive charges. You all know that inside the nucleus, this is the nucleus. Okay. Now the radius of the nucleus is capital R, and inside the nucleus, you know, protons are there, and Ze is the total charge inside. So let's say it is not a surface charge distribution, it is a solid charge distribution. And let's assume that this charge, these positive charges are uniformly distributed everywhere inside this particular sphere. This is the nucleus. Now what you're supposed to do is, what will be the force that this positive nucleus exert on an electron placed outside and inside. If the electron is outside, what is the force it will experience? If the electron is inside the nucleus, what is the force it will experience? So this is what we are going to now see. So I'll just clear up this place so that it looks cleaner. Let's try how to do this problem. So let me just draw. So this is your nucleus. What is the radius of the nucleus? What's the radius of the nucleus? Capital R. And what is the total charge? It is plus Ze. Z is the atomic number. Okay. Now, you want to find what is the force exerted on an electron placed outside. Placed outside. That means placed at a distance small r greater than capital R. So what did shell theorem tell you? Shell theorem told you that any shell can be treated as a point charge. When you take a point charge and keep it outside, any uniform shell can be treated as a point charge. So now look at this. This is made up of a number of shells. This is made up of a number of concentric shells. So what you can do now is, you can treat that each shell becomes a point charge at the center. Each shell becomes a point charge at the center. So this becomes equivalent of saying that there is a charge Ze at a distance r from the electron. That is, the spherical charge distribution can be treated as a point charge. So therefore, for r greater than capital R, what will be the force? You just apply your Coulomb's law straight away. So what will it be? 1 by 4 pi epsilon naught Ze into charge of the electron divided by r square. Or I will say it is 1 by 4 pi epsilon naught Ze square by r square. And it is going to be an attractive force. So we can put an arrow here and say it is an attractive force. Okay. Now, what happens for r less than capital R? What happens for r less than capital R? Meaning, we see this. Assume it's a uniform charge distribution. Find the force experienced by an electron at r less than capital R. R less than capital R means you are here. Your charge electron is here and it is at a distance small r less than capital R. That means it is inside the nucleus. It cannot happen normally Okay, when it can happen is when you are doing particle physics experiments, at high speeds, if you allow an electron to hit a nucleus, it can enter the nucleus. Otherwise, you don't find an electron inside a nucleus. So what will be the force that this electron experiences? Okay, for that, what we have to now do is, we have to now construct a sphere of radius small r. Construct a sphere of radius small r and consider all the charge inside this sphere. Why should you consider charges inside the sphere? Anyone? Anyone?
There are shells inside that sphere.
Right. There are shells inside that sphere. To all those shells will become point charges at the center. But shells which are outside small r, they will not be seen by the electron. They will not be seen by the electron. Okay, so what you have to now do is you have to say that F is equal to 1 by 4 pi epsilon naught, and we don't know how much is that charge. So let us call this charge as some q prime. Let us call the charge inside this green sphere as q prime. So we write 1 by 4 pi epsilon naught q prime into E divided by r squared. Okay, but we don't know what is q prime. So what is this problem saying? It says that the charge distribution is uniform. There is a volume charge distribution that is uniform. So what now you have to do is, what is the charge present inside this volume 4 by 3 pi small r cube? What is the charge present in the total sphere? Charge present in the total sphere will be equal to ZD. So ZD divided by 4 by 3 pi capital R cube is the volume charge distribution. Are you understanding this step, guys? Z is total charge. So total charge divided by total volume is the charge distribution, charge per unit volume. Now I want my Q prime. So what will be my Q prime? Q prime will be equal to rho into 4 by 3 pi small r cube. It is like this. Cost of 20 chocolates, cost of 1 chocolate, cost of 2 chocolates. So I give you the cost of 20 chocolates, and if I ask you the cost of 2 chocolates, what do? You find the cost of 1 chocolate. Then multiply by 2. Then you get the cost of 2 chocolates. Similarly here, I know ZD is the total charge in the big sphere. Okay, so I want what is the charge distribution, that is cost of 1 chocolate. So that's going to be ZD divided by 4 by 3 pi r cube, capital R cube. Then I want what is the charge inside that small sphere. So what do? Charge distribution into the volume. Okay, so now I can just expand it. I can write ZD divided by 4 by 3 pi capital R cube into 4 by 3 pi small r cube, 4 by 3 pi, 4 by 3 pi goes. Okay, so I'm just going to use it here. So this becomes 1 by 4 pi. My God, I'm always going below the Lakshman Rekha. Okay, therefore, F becomes equal to 1 by 4 pi epsilon naught. So instead of Q prime, what do I write? I write ZD R cube by capital R cube. So that is why charge Q prime. Okay, so that I put, then I put E divided by R square. So simplify it and tell me what will it become? 1 by 4 pi epsilon naught into Z E square, then
R divided by R cube.
R by small r divided by capital R cube. Or you are finding that the force is directly proportional to the distance from the center. All other things are constant here. You see, all the things are constant. Okay, only this cube looks like 3. There is a chance that somebody will read it as 3. Okay, so you see that force is proportional to the distance from the center as long as you are talking of points within the sphere. As long as you are talking of points within the sphere. But when you are talking of the electron outside the sphere, outside the nucleus, then you see that force is proportional to 1 by r squared. Okay? So can someone plot this? Can someone make a plot of, so You should be able to see everything as a graph. Force versus distance from the center. Okay, you can stop at R. So this is less than the radius and this is region greater than radius. So can you plot it? Look at this. Let us first of all talk about inside the sphere. So when R equal to 0, what is the force? Look at this. When R equal to 0, what is the force? Small r equal to 0?
0.
0. So that means it starts here and it is going to be a straight line graph because it's directly proportional. So proportional to 1 by R. But once you reach the surface, what is happening from here onwards? It is going to fall off as 1 by small r square. So 1 by small r square will look like this. So for anything like this, you should know how to draw the graphical representation. You should know. Okay. So now we have done this problem assuming that the nucleus is having a uniform distribution of protons. Now let us go ahead and look at another situation. Find the same forces, find the forces, then the charge distribution is a function of R. The charge distribution is a function of R and B is a constant. B is a constant. Okay. So what does this mean? This is like this, I am having a sphere. Let's say I'm having a sphere and I'm finding that the charge distribution is directly proportional to R. So inside the charge is sparsely put, but as you go outside, the charge becomes closer. As you go outside, it becomes still closer. And outside, it is very, very dense. Are you able to understand this picture? Inside, the charge distribution is 0, but as you keep going outside, the charges are closer and more clustered together. So that's the meaning of this expression. So let us say that nucleus is having this kind of a charge distribution. So first of all, let us consider for small r greater than capital R. There is nothing to do. Straight away you know that F is equal to 1 by 4 pi epsilon naught Q E square by R square for R greater than capital R. You know this is the case because you know that the total charge inside is only ZE. But now let us go to for R less than, I can put an equal to also here, for R less than capital R, what will happen? Let us see. For R less than capital R, let us put my electron here and then draw an imaginary sphere here. Let this be smaller. Now, can you find out Q prime? Let Q prime be the charge inside this shell, inside this small sphere. Therefore, how will I write my F? F will be equal to 1 by 4 pi epsilon naught capital Q prime E divided by R square for R less than capital R. That is when the electron is inside the nucleus at a distance smaller from the center. But can you find out Q prime now? Can you find out Q prime like how you did in the previous case?
No, ma'am.
Why?
The charge is not uniformly distributed.
Charge is not uniformly distributed. Charge is not uniformly distributed. So now you have to do calculus. So what is it? I will just briefly explain to you. So let us say that I have a sphere. Let's say I have a sphere and let us say that there is a radial symmetry. This is called radial symmetry. That is with distance from the center, there is a symmetry. Okay, so that's the meaning of radial symmetry. So let us say that you can divide this distance, this is capital R, let us say, you can divide this into a number of concentric shells. You can divide this into a number of concentric shells and the shells should have some radius small r and a thickness equal to dr. Okay, each shell is going to have some radius r is a variable, and thickness of the shell will be dr. And dr should be so small that the charge distribution in that shell should be uniform. dr should be so small that the charge distribution variation should not be there with thickness. Okay, it should be so small. Then what do? Find out what is the charge on this shell. Find out what is the charge on this shell. Let dq be the charge on the shell. Can you tell me what will be dq? dq will be on this shell. I know what is the charge distribution per unit volume, that is rho of r. Okay, and what is the volume of the shell? Not inside, just the shell. What is the volume of the shell?
Pi small r square dr.
4 pi r square dr. It is three-dimensional media, so it's not pi small r square. It will be 4 pi r square dr. You have to take the surface of the inner surface of the shell, then multiply by the thickness. Therefore, it is 4 pi r square dr. Did you understand this? Okay. Therefore, what is my rho r? Rho r is dr. Then 4 pi r square dr. So this is dq. Now I want the total charge in this radius small r. So what do I do? If I want my q prime, I can say q prime will be equal to, do the integration from 0 to small r. 0 to small r of dq, which will be 0 to small r dr 4 pi r square dr. Okay, or this will become 4 pi d into r to the power of 4 by 4, or that will be pi d r to the power of 4. So this will be q prime. So let's put that into the above equation. Therefore, force will become 1 by 4 pi epsilon naught into pi d r to the power of 4. So that is q prime. Okay, then into E divided by r squared. Okay, so this is the way you can do these problems. So here I am assuming B is some constant. I am not trying to find out B. Can someone tell me how to find out B? If I am interested in finding out B, how should I find out B? I can even find out B and put it into that equation. Can someone tell me how to find out B? What is the total charge in the entire sphere? It is ZD. So ZD by the same logic can be obtained by doing 0 to capital R, 0 to capital R, rho of R, 4 pi R square dr. Okay, if I do this, I can actually be able to get my B. In fact, somebody can try it and see what your B will be. B will be on the right hand side of the equation, or I will just write it's going to be equal to B into capital B into pi capital R to the power of 4, okay, is what you will get. Instead of small r, it will be capital R here. Okay, that will be equal to ZE. Okay, therefore B will be equal to ZE divided by pi R to the power of 4. Okay, that B you can substitute here and get your force. This is complicated. I know that this kind of problems will not be asked in an examination for you, but then for the sake of understanding, this problem has been given in the book. Okay, one is if it's a uniform charge distribution, very easy to get what is the charge inside. If it is not, you have to do integration. Okay, now technically this chapter is over, but very quickly let us try one or two problems. So shall we try this? Just try this. Here's an exercise problem, try it. So there are two charges Q1 and Q2. This is the first picture, Q1 and Q2 at a distance d from each other. Okay, if Q1 equal to Q2 is equal to 21.3 microcoulomb and d equal to 1.52 meters, what is the electric force that acts on Q1? Tell me, how will you do that? F is equal to? F is equal to?
Q by R square.
KQ by R
Q
square.
square by R square.
KQ by R square. K is 1 by 4 pi epsilon naught. K into Q1, Q2 by D square, which is K Q square by D square. Okay, so substitute 9 into 10 to the power of 9 into what is Q1 equal to Q2 is equal to 21.3 micro. What is micro? 10 to the power of minus 6 whole square. Then what do you have? Divided by D square. So what is D? D is 1.52. So 1.52 whole square. Okay, so if you use your calculator and do it, you should get an answer 1.767 Newton. Okay, so this is over. Now, this B part, if you can do, I will be convinced that whatever you have learned in these last 2 days, you understood. If you can do this B part. What does B part say? B part says, now put a third charge Q3, also equal to 21.3. Okay, so that it forms a equilateral triangle. Now, what is the force on Q1? What is the net force on Q1? So, how will you do that? Which is the principle you have to use?
Superposition.
Principle of superposition. Therefore, F1 will be equal to F12 plus F13. By now, you know that the value you know. The value is because it's after all the same Q, same D. Therefore, you know the value. But then you have to vectorially add them. So how do you vectorially add them? You have to first of all see what is the direction of F12, what is the direction of F13. So let's do that. What will be the direction of F12? Will it be repulsive or attractive?
Repulsive.
Repulsive, repulsive. So let me just put an arrow like this. So this is F12. And this angle is going to be 60 degrees. Okay. Similarly, what will be F13?
Repulsive.
Repulsive. F13 is also repulsive. Sorry. F13 is also repulsive. So let's just draw that repulsive. So with repulsive along this line itself, you draw one line. So this is going to be F13. Okay. Now how do you add these two? How do you add these two vectors which are having the same length? And what will be the angle between them?
60.
The angle between them will be 60. The angle between them will be 60. Okay. Therefore, how do you add them? So F12 is going to have components. What will be the direction of the components? One component will be like this, and the other component will be like this. Okay. Similarly, this F13 also it will have two components. One component in this direction, and the other component in this direction. Now these two will cancel out. These two will cancel out. Now this angle will be 30 degrees. This angle also will be 30. Okay. Therefore, what will be the net F? F1 will be equal to, is cosine component or sine component? If I have a vector like this and I talk about this angle, so which component is this? Cosine or sine
component?
This is my F. I am talking about what is this? If this is theta, and if this is my F, this is the base, right? This is base. So will it be sine or cosine?
Cosine.
Cosine. Therefore, there will be two such cosines coming. There will be two such cosines coming. 1.767 into cosine of 30 into 2. Are you getting this point? In case there is still some doubt, I will just draw it, a big figure I draw. Okay. So you are going to have two vectors like this. One is F13, the other is going to be F12. Both are having the same lengths. Okay, and you can see that if you add two vectors like this, okay, then they are going to have components. One component is going to be like this, and another component will be this for F12, and one component will be like this, and another component will be this for F13. Now these two fellows will cancel out, and this is 30 degrees. This is also 30 degrees. Okay, F12 and F13 are hypotenuse of the right angle triangle. Hypotenuse of the right angle triangle. Therefore, this vector is simply going to be 2 times F, let us say F12, 2 times F12 cos 30. 30 because this total angle is 60. Is this clear, guys?
Yes, ma'am.
That's it. Please always, I know students have a problem with sine and cosine. Please treat the vector whose components you are trying to find as the hypotenuse of the right angle triangle. Okay, that becomes a hypotenuse. And with respect to that, look at where your theta is and then try to draw the third side. Then you know that this is the base. Therefore, cosine. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay, now let's try this one. Let's see this. Three charged particles lie on a straight line and separated by distance d. Q1, Q2, Q3 are there. The distance between each of them is happening to be the adjacent ones is d. They are kept fixed. Okay, and it says Q1. I'm sorry, guys. To be in equilibrium under the action charge 3, which is free to move, is found to be in equilibrium under the action of. Let me find Q3. Okay, fine. Okay, so the problem goes like this. You have 3 point charges Q1, Q2, Q3, and when placed like this, it is found that charge 3 is in equilibrium. Q1 and Q2 are kept fixed with a distance d between them. When you put a charge Q3 on the same line, Q3 comes to rest at a distance d from Q2, implying Q3 is in equilibrium. Do you know what's the meaning of equilibrium?
Net force is 0.
Net force acting on it is 0. The net force acting on it is 0. So what are the two forces acting on it? When can it be equilibrium? It can be equilibrium if the two forces acting on it are equal and opposite, right? So let us first draw two arrows on it, one in this direction, one in this direction. Okay, so let's say one force is F13 and the other force is, what is it? Sorry, made a mistake here. What is the mistake I made? So what should I write here? F31. Force on 3 because of the first force. Then what will this force be? Force on? Force on?
3
3
to 2.
Force on 3 because of 2. Now sum of these two should be equal to 0. Okay, so let's write this. F32 plus vectorially I'm writing F31 equal to 0. Then only you say that this charge is in equilibrium. Now you have to find out what will be Q1 in terms of Q2 for this to happen. At this distance.
Q2 minus 4 Q2s.
So let us do one thing. No? Let us do one thing. Let us take one direction as the x-axis direction positive, and the opposite is going to be negative. Okay. So let's say F31 is positive. If F31 is positive, then it becomes 1 by 4 pi epsilon naught. Then 31. So Q3, Q1 divided by, what is the distance between them? 3 and 1. What is the distance?
2D.
What is the distance? 2D. So I'll say 2D squared. Okay, so let's say this is positive. Then the opposite one, F32 will be negative because it's in the opposite direction. So let's put a minus sign here and write that force also. 1 by 4 pi epsilon naught. So what do I write? Q3, Q2 divided by D square. So sum of these should be equal to 0. So from here, what can you write? From here, what can you write? Q3 can be neglect or can be cancelled out. 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught can be cancelled out. D square and D square can be cancelled out. So you will get minus Q2 plus Q1 divided by 4 equal to 0. Am I getting that?
Yes, ma'am.
Right. So now what do I get if that's the case?
Q1 equals to 4Q2.
Q1 equal to 4Q2. Is this right? No, there is a minus sign missing. What's happening here? Tell me. There should be a minus. Because if both these are, let us say, positive, having the same sign, these forces cannot be in opposite direction. So one of them has to be positive, the other has to be negative. So are we missing something?
Well, you already assumed the charge in a map. When you
What is
found
that?
out Q2.
What is that?
When you said Q2, when you put negative on force due to Q2, you already assumed that Q2 would be on opposite direction. So now you found magnitude without charge, without sign.
Okay, so I need not put this. That's what you're trying to
Yes,
say? Okay.
yes, when Q1 Q2 have same sign, then you will.
Yeah, so you will get Q1 equal to minus 4Q2. Okay, so from here you are able to get Q2 in terms of Q1 or Q1 in terms of Q2, and you're seeing that they have to be necessarily of opposite sign. They have to be necessarily of opposite sign, only then you can have this kind of a configuration. Okay. Okay, let us try one more problem. Let's try this. You have a square. You have a square of side A. You have a square of side A, and there are 4 point charges plus Q minus Q plus 2Q minus 2Q at the 4 corners. Find the net electrostatic force on plus 2Q. On plus 2Q. How will you do that? Put it here. Let me also increase the size. So which principle what should you use here to find out the net force? So what is it supposed to find? Find the net electrostatic force on plus 2Q. Plus 2Q. Instead of writing Q minus Q and all, what I will do is I will just give these fellows one number. I'll call this as 1, 2, 3, and 4. Okay. So are we going to find F1, F2, F3 or F4?
F4.
F4. We are going to find out F4. So F4 is going to be equal to
F41 plus F24
No,
42 plus
no, 4 to
F34.
4 to that order is very important. Force on 4 because of 2. 4 2 plus
F43.
4 3. Okay. Okay. Now on 4, let us draw these 3 arrows and show. Okay. What will be the direction of F41? F41. Will it be attractive or repulsive?
Repulsive.
Repulsive. Okay. Repulsive. So this is going to be F41. Okay. Next, F42. F42 will act along the diagonal. Along the diagonal. Okay. So will it be attractive or repulsive? What happened to the girls today? Nobody's talking. Will it be attractive or repulsive?
Attractive.
Attractive, because they are opposite signs. So they are going to be attractive. Yes. Then, what is the third one? Third one is between 4 and 3. 4 and 3. Will it be attractive?
Yes, ma'am.
Yes, attractive. Okay, so let's put that. F4, 3. Yeah. And you know that now we have to immediately give a direction. Okay, let's call this as I cap direction. Let's call this as J cap direction. Okay, so what will be F41? Tell me. F41 will be K into 41. So 2Q and Q. So therefore it will be 2Q square divided by A square. And along which direction? Along the minus J cap
Minus.
direction. I'm sorry, plus J cap. Hey, what did I do? One sec. Let us keep the convention without spoiling IJ. Okay. Therefore, it will be along minus J cap direction. Now, let us come to the last vector. Okay, let us come to the second vector. So, what will be the second vector? 4, 2. 4, 2 means it will be K into 2Q square. Don't put minus, okay? Don't do that multiplication. So, just write 2Q square divided by, what will this distance be?
Root 2a.
Yeah, root 2a. When you square it, it becomes 2a square. And now you have to write I and j component for this. You see this vector? How do you write the I and j component? It will have a positive j component and a positive I component. And this angle is going to be 45 degrees. So therefore, what will be the I component? I component will be base of the right angle triangle. Therefore, cos 45 cap, then plus sine 45.
J.
Then what will be the third force? F43. F43 is again along the positive I cap direction. Therefore, I write positive. Then K I put. Then after putting K, what should I do? Multiply the forces. What are the forces? Plus 2Q and minus 2Q. Don't take the sign. Directly multiply. So it will be 4Q square divided by distance is A. So A square and direction is I cap. So basically I wanted to just put these steps for you to understand that you should not multiply the sign of the charges. Don't multiply the sign of the charges. Multiply just the modulus of the charges. And after that, the direction you should take into account by seeing whether it is repulsive or attractive. And always put the arrow on the charge that is going to experience the force. Put the arrows on the charge that is experiencing the force. Here you are asked, what is the net force on 2Q plus 2Q? So that is your charge on which your arrows should come. And then you have to look at each pair of forces and see each force between pairs of electrons and pairs of charges and see whether it is attractive or repulsive. And then draw your arrows. Now from here, I'm sure anybody can finish it, right? This is I cap. I cap. Now can't you do this? Cos 45 is 1 by root 2, sin 45 is 1 by root 2, then add up the I components, add up the j components. You get the force. Yes or no? Can you do these kind of problems?
Yes,
Yes.
ma'am.
Right. So I think we have come to the end of the chapter. That's it. So the chapter is done. Any doubts that you want to ask? Any doubts? Only 41 of you. That is very, very disappointing. I've been talking to the other sections also. Better attend classes tomorrow. If you are stopped from writing exam, don't blame us. Okay? Oh, somebody is giving attendance now. Okay. From tomorrow, give your attendance like this in every class. 41. So I will only consider 41. Any doubts, guys? No, ma'am. Akshara, are you reading every day? I find you little active. Are you studying?
Yes.
I really feel sad that we are not having a class, where we can interact face to face. Because, with that limited space, with that pen and all, there is only so much one can do. I'm trying to color coordinate and use different colors to make it appear. I don't know how you are seeing. And especially, please, you have all been given laptops. For heaven's sake, use your laptops. Use your laptops. And please don't give proxy for others, because if you do that, then your numbers we know. Okay? And these transcripts of every class, this is also getting saved. So hereafter, give your attendance here only. I hope you're all giving your attendance. 41 of you, please give your attendance. Later, don't blame me if your attendance is not there. I was taking screenshots, but now I think I'll go with this. At least there is a proof. Okay, if all of you have given your attendance, you can leave, and from next class, we'll be starting chapter number 26. Be ready for a quiz also. Prepare for a quiz. Okay? So how was Holi? Anyone celebrated? And as promised, I'm keeping my class to 50 minutes only. Abhinav. Okay. So tell me guys, how was Holi? Will our timetable change, madam? No, there will be no change in timetable. We'll continue like this only. Okay, there's nothing to ask. We can, cause we have classes like 3 days in whole week. Yeah, but that's what it's supposed to be, no? Acha, why you are having classes for only 3 days is what Kaladar is asking. That is because in a normal situation, you should have been having fewer classes and labs. But where labs are not there, no. Today you will come for a lab, you will see that even labs you are supposed to do only like this online. And please, when you come for the lab, please come with everything that we have said. Please read and come. We'll explain, then you're supposed to read it. Section 2 and section 3 students, by tomorrow night 10 o'clock, you should have uploaded your lab work. Okay, keep that in mind. Any deviation from that will not be accepted. Okay then. Good day.
Thank you.